Hi class, welcome back to thermodynamics. In this lecture, we're going to start by looking at the third statement of the second law of thermodynamics, which starts to look more deeply at entropy, and today we're going to be defining entropy as a property, and we use the variable S to stand in for entropy in thermodynamics. So now, begin looking at the third statement. It says that delta S, so the change in entropy contained in the system for some change in time, for some time duration, that's what that T is, time, is going to be equal to the entropy transferred in across the boundary for that same time duration, delta T, plus the entropy S produced in the system for that time duration delta T. Now, the entropy that's transferred into the system across the boundary, it usually accompanies Q. When we're dealing with control problems, so mass flow rates, then this also accompanies matter. So for control volumes, this also accompanies matter. Okay, so returning to our definition of entropy, entropy measures disorder within a macroscopic, so large scale system, and it also explains the number of microscopic configurations, or quantifies the number of microscopic configurations. So as has been said several times at this point, entropy never decreases in an isolated system. So for example, if you have marbles in a box and you don't put any energy in to organize them in any way, they're not going to magically sort themselves out in rows according to color. For example, they're not going to ever organize themselves spontaneously. Now, entropy can be created but not destroyed, and entropy is also a quantification of energy quality, right? So when we get an increase in entropy, we get a decrease in the quality of our energy. And the quality of energy matters because that gives us the ability to do useful work. So heat is a degraded form of energy. We can get less useful work out of it. So now going back for a second to last lecture when we were looking at the Clausius inequality. So the change in entropy is going to be equal to the infinitesimal heat transfer divided by the temperature of the systems across the boundary, the temperature of the surroundings, across the boundary for an internally reversible process. So remember that sigma cycle is 0 if it's reversible. It's greater than 0 if it's irreversible. If it's irreversible. And it's less than 0 if it's impossible. And that is for the Clausius inequality, right? Which is if you look at del Q over T over a whole cycle across the boundary, that's going to be equal to minus sigma cycle. Okay, so now we're starting to put these pieces together. Now, entropy, the units for entropy are going to be for the extensive property of entropy, that's capital S, is going to be in joules per Kelvin. For the intensive property, that's lowercase s, it's going to be joules per kilogram. Okay, right, on a mass basis, if it's an intensive property, per Kelvin. Okay, and the thing is, we can look up entropy in our property tables. So if we were going to look up entropy in the saturation tables, the liquid vapor saturation tables, so what we would do is we have to know the quality X. So we use the saturation data, and X is the quality. So just the same thing that we've done with quality, with specific volume, with internal energy, with enthalpy. For entropy, S is going to equal 1 minus X. Remember, X being 0 tells you that you have a saturated liquid. X being 1 tells you that you have a saturated vapor. So 1 minus X gives us the proportion of liquid plus X times the entropy if it were 100% vapor. So I'm just going to pull up the tables for water for 1 second. So looking at this is from your book. You can see that in the under the vapor dome for the saturated liquid vapor tables, we still are looking at these same tables that we've been using for specific volume, internal energy, and enthalpy. But now we'll be looking at lowercase s. So this is our intensive property, right, on the mass basis. So this is kilojoules per kilogram Kelvin. So that's the per Kelvin. The Kelvin's in the denominator in your table. So if you had a saturated liquid, you'd be over here. So there'd be 1 minus the quality times the saturated liquid value, and then X your quality times the plus X times the saturated vapor value. And we'll be working with that a little bit more later today. And now looking at liquid. So for liquid, what you're going to do is you're going to still use the saturation tables. To look up entropy. And the way this is going to work is you look up entropy. So entropy for some temperature and pressure can be approximated by the entropy of the liquid in the tables at that temperature. Okay, so when you have a liquid, all you do is you look up SF in the saturation tables at the temperature that you have. And so now I'm going to introduce two new types of diagrams to you. Here we have the temperature entropy diagram, and this is an example for water. So we have the critical point at the top of the vapor dome, right? So for reference, that's about 0.01 degrees Celsius or 32.02 degrees Fahrenheit. And for refrigerants, it'd be minus 40 degrees Celsius, which is the same as minus 40 degrees Fahrenheit. And so under the vapor dome, P is constant would be this line, right? Because temperature and pressure are coupled under the vapor dome. And so what these P's here, P1, P2, P3, P4, are showing you what various isobars, so lines of constant pressure, what they look like on a temperature entropy diagram. And so then, for example, so down here we have solid vapor region, which is ice and steam. Over here we have our liquid region, we have our critical point, and then we have our steam region over here, and our mixed is of course under the vapor dome. And another thing we can look at is a line of what would it look like if specific volume were a constant. So specific volume being a constant would look something like this. So this would be specific volume being a constant. And enthalpy being a constant would follow a line something like this. This would be H equals constant. Okay, just to give you a sense of how these constant lines look on a temperature entropy diagram. Now, to the right here, we're looking at an enthalpy entropy diagram. So once again, we have our vapor dome. So here's our vapor dome. Okay, and I'll just highlight it here as well, our vapor dome for comparison. And our critical point is down lower now. Our critical point is here on the enthalpy entropy diagram versus up top. So this is another view. Okay, so enthalpy versus entropy. So this would be a line of constant dryness, and our isobars, or our lines of constant pressure, look more linear on this diagram. And so what we're looking at with these other bars that you don't see in the other diagram, and I'll highlight them a different color. I'll make them pink. So these lines right here, that would be an example of T equals constant. So those are our isotherms. And as you can see, under the vapor dome, right, our lines of constant pressure are isobars, and our lines of constant temperature, our isotherms, are right on top of each other, right, because they have a coupled relationship under the vapor dome. And this type of diagram, the enthalpy versus entropy diagram, is known as a Mollier diagram. All right, so let's move on, and we'll get into some exercises very soon. But first, we're going to look at the energy balance for a simple compressible system. So for this, the infinitesimal Q, heat transfer, for an internally reversible process is going to be equal to du, the change in internal energy, plus del W. So the infinitesimal work for the internally reversible process. So T ds is going to be equal to this del Q for an internally reversible process, because if you remember from our definition, previously ds is equal to del Q over T, so we're just multiplying both sides by that T. So TDS is going to be equal to du plus PDV. Okay, so we're just subbing in PDV for our del W for an internally reversible process for a simple compressible system like a piston cylinder that is being compressed very, very slowly. So then we can go ahead and let's sub in enthalpy is equal to U plus PV. So change in enthalpy is going to be equal to du plus dP times V, which is going to be du plus PDV plus VdP. Okay, so we're just expanding out. And notice that du plus PDV is, once again, TDS. So dH is going to equal TDS plus V dP. So TDS is going to equal dH minus V dP for a simple compressible system. Okay, and so we are going to use this relation in the next couple exercises. So let's have some practice. And to do so, let's start. We're going to move on to chapter 6 in your text. And let's look at number 10. Propane undergoes a process from state 1, where the P initial is 1.4 megapascals. And I'm going to start jotting down the givens below. So P1 is 1.4 megapascals. T1 is 60 degrees Celsius. To state 2, where P2 is 1 megapascal. And during which the change in specific entropy, so over this process, so from 1 to 2, S2, minus S1 is going to be equal to minus 0.035 kilojoules per kilogram Kelvin. So at state 2, we need to determine the temperature in degrees Celsius and the specific enthalpy in kilojoules per kilogram. So we're tasked with finding T2 and H2. Okay, so let's go through this. So what we can do is we can start by looking at our property tables for propane, and we can look up the entropy for state 1 and state 2. So let's open up our property tables. Let's go to propane, which should be A18. Keep scrolling. Okay, so now for propane, we are starting at a pressure of 1.4 megapascals and 60 degrees Celsius. So let's look at superheated, since that's a pretty high temperature for propane. So 1.4 megapascals. And yep, Tsat is 40, almost 41 degrees Celsius. So at 60, we are going to have an entropy of 1.845 kilojoules per kilogram Kelvin. So from table A18, we get that entropy is 1.845 kilojoules per kilogram Kelvin. Okay. And we know the difference between S2 and S1. So we can find S2 now that we know S1. So S2 is going to equal S1 plus, well, S1 minus, sorry, 0.035 kilojoules per kilogram Kelvin, which is going to be equal to 1.845 minus 0.035 kilojoules per kilogram Kelvin, which is going to give us 1.81 kilojoules per kilogram Kelvin. Okay, so we know our entropy for state 2. All right, so now what we need to do is we can go ahead and look up what T2 and H2 must be. So let's open up our tables. And we need to find for a pressure of 1 megapascals. So 1 megapascal. Okay, and we need to see if we can find 1.81. Yes, so we have the entropy here on our superheated diagram. Okay, so that matches up with a temperature of 40 degrees Celsius and also an enthalpy of 524.6 kilojoules per kilogram. So that is it for this one. So just looking it up in the tables for pressure of 1 megapascal, we have T2 is 40 degrees Celsius and H2 is 524.6 kilojoules per kilogram. So if we just wanted to do a little sketch of this on a TS diagram. So we're in the superheated. So I'm just going to draw our vapor dome over here. And we're going to look at entropy in kilojoules per kilogram Kelvin. And T is going to be in degrees Celsius. So we started at 60. We ended at 40. And for entropy, we ended at 1.81. And we started at 1.845. So here's state 1. And here's state 2. And I'll just sketch on the isobars. They would just look something like this. So those are the lines of constant pressure. All right, so let's move on and do one more. And this one's a little bit longer. So 1 kilogram of water in a piston cylinder assembly undergoes the 2 internally reversible processes in series, and we're going to draw those in a moment. And for each process, we need to determine in kilojoules the heat transfer and the work. All right, so I'm going to draw this on a TS diagram to give you the information. So this will be 1. This will be 2. And 3 will be over here. Okay. So here's the info. So P1 is going to be 0.1 megapascals. T1 is going to be 100 degrees Celsius. This right here is going to be a line, this is following a line of constant entropy. So this is S equals constant. And here is going to be an isobar. So this is P equals constant from 2 to 3. And then we're going to end with P3 being 1 megapascal. And T3 is going to be 400 degrees Celsius. And so we're given that this is going to be water in a piston cylinder. Let's give this a little draw. So this is H2O, and we have 1 kilogram. And we have that this is 2 internally reversible processes in series. And we need to find Q and W for each process. Okay, so we have process 1 to 2 and process 2 to 3. So let's start. Okay, so let's look at process 1 to 2. So we'll start with an energy balance. And from 1 to 2, we have Q minus W is going to equal delta U. Okay, so something that we know about this process is that S1 equals S2. So entropy is constant. And in that case, that is telling us that Q is that heat transfer is 0 because delta S is 0. Okay, so that's that assumption right there. That's because delta S is 0. All right, so we end up with minus W equals delta U. So work for process 1 to 2 is going to equal minus M times U2 minus U1, or just M times U1 minus U2. Okay, and so we know we're dealing with water here, and so now let's just look up all the associated information for, since we have T, we have P, so we can look up V1, U1, S1 in table A4. Let's go to table A4. Okay, and we know that we have a pressure of 0.1 megapascals and a temperature of 100 degrees Celsius. So 0.1 megapascals and 100 degrees Celsius. We are in fact in superheated land, and so we have our specific volume, we have our internal energy, and we know our entropy. So let's write all that down. So from A4, we get that V1 is 1.696 meters cubed per kilogram. We get that U1 is going to be 2506.7 kilojoules per kilogram. And we get that S1 is going to be 7.3614 kilojoules per kilogram Kelvin. Okay. And so another thing we know is that S1 is equal to S2. And we also know that P2 is equal to P3 because P equals constant over the process from 2 to 3. So P2 is equal to P3, which is 1 megapascal. So from this, we can find T2. So we have to open our table back up, and we need to find 1 megapascal. Okay, and we need to find something close to 7.3614 kilojoules per kilogram Kelvin because S1 is equal to S2. So we're going to be somewhere between 360 and 400 degrees Celsius. So we need to interpolate. And I'm going to open up a new sheet for that. Okay, so T2 is going to be 360 degrees Celsius plus 7.3614. So that's the entropy that we have for S2 minus the lower limit in our table, which is going to be 7.3349 divided by the upper limit, 7.4651 minus 7.3349 times the difference between the two. So our lower limit temperature was 360, our upper limit is 400. 400 minus 360 is 40. Which is going to give us 368 degrees Celsius. Okay? And so then, now we can go ahead and figure out what U2 needs to be following when we're going to also have to interpolate for that. So U2 is going to be 2891.6, and this is going to be in kilojoules per kilogram, plus 7.3614 minus 7.3349 divided by 7.4651 minus 7.3349 times our difference in internal energy now between the upper and lower limits here. So it'd be 2957.3 minus 2891.6. 2957.3 minus 2891.6, and this is going to be in kilojoules per kilogram. And that is going to give us a U2 of 2905 kilojoules per kilogram. And so then we can go through and we can calculate work now for our first process, which is going to be equal to minus M times U2 minus U1, which is going to be minus 1 kilogram, times 2905 minus 2506.7 kilojoules per kilogram, which is going to give us minus 398.3 kilojoules of work done on the system. Okay, and so now let's move on to process 2 to 3. Okay, so this is going to be 2 to 3. Okay, so once again, we know that P2 equals P3, which is a constant. And so that tells us for an isentropic process that N is 0. So W23 is going to equal P delta V, which is going to be MP times the change in specific volume, so little v3 minus v2. Okay, and so v2, once again, we are going to need to interpolate to get. And so to save some time, this whole ratio right here, the 7.3614 minus, so the change in entropy of where we're at compared to the lower and upper limits in the table for state 2. So So that ratio is 0.2035, this ratio right here. So I'm going to just use that to save some time and energy with writing. Okay, so this whole thing right here is 0.2035. Okay, so more interpolation, lots of interpolation in this example. So V2, we're going to look in the table at the specific volume for our lower limit, and that's going to be 0.2873 plus that ratio, which is 0.2035, okay, times the difference for specific volume for our upper and lower limits, so 0.3066 minus 0.2873, and this is going to be in meters cubed per kilogram. So V2 is going to be 0.2912 meters cubed per kilogram. And then we can go ahead and we can look up V3 in the tables. So V3 is for 400 degrees Celsius and 1 megapascal. So V3 is going to be 0.3066. So then we can calculate work for 2 to 3, which is going to be 1 kilogram of water times the pressure, which was 1 megapascal, which is equivalent of 1,000 kilopascals, times V3 minus V2, so 0.3066 minus 0.2912 meters cubed per kilogram. And so we end up with 15.4 kilojoules. And let me just go back here and make this completely clear, because we're supposed to find work and heat transfer for each process. So Q12 is 0 kilojoules because delta S is 0. Okay, almost there. So now we just need to find Q23. So Q23 is going to be M times U3 minus U2 plus W23, just doing an energy balance here. And so U3, we can just look up in the table, and so let's practice looking it up. So for, once again, 400 degrees C, 1 megapascal, so U is going to be 2,957.3 kilojoules per kilogram. So U is going to be, U3 is 2,957.3 kilojoules per kilogram. Okay, and so this is going to be equal to 1 kilogram times 2,957.3 minus 2,905, and we figured that out earlier. This is kilojoules per kilogram, plus 15.4 kilojoules. So Q23 is going to be 67.7 kilojoules. Okay, that is it for this lecture. So I will see you next time.